In this video, I'm going to go through the first page of the 1-1A lesson, Simplifying Expressions and Algebra Tiles. The first thing we're going to do is review sets of numbers from 7th grade. The first set, and we're kind of going from smallest set to largest set. So the first set that we learn when we're a child is something known as natural numbers or counting numbers. I'm going to abbreviate. Feel free to abbreviate as well. And I'm going to use set builder notation to list these out, which is a fancy brace where we're going to list out some of the numbers. So this would be 1, 2, 3, 4, 5, 6, ... You did sets like this in 7th grade with probability when you would have a sample space and you would flip a coin and you might talk about how the sample space would be in set builder notation, either heads or tails as the possible outcomes. So we'll do the same thing with sets of numbers. So you'll notice that this does not include 0 because generally when you're learning to count, you generally don't learn to include 0. I guess if you did, then you learned about whole numbers before you learned about natural numbers. So this is the set of counting numbers and 0. And you'll notice that we have not dealt with fractions or decimals other than that if we had 15 thirds, this equals 5. So if it simplifies down to a whole number or a natural number, fractions or decimals are permitted in these two sets. But if it doesn't simplify down to a whole number or a natural number, then it's going to fall into the other categories. Next set is integers, which is whole numbers and their opposites. And so if we go back to whole numbers, we were only talking about the right half of the number line, and we'll draw out some number lines in some of the upcoming lessons. And so C unleashes the left half of the number line. So we'll do a brace, ... -3, -2, -1, 0, 1, 2, 3, ... And we're still skipping over fractions and decimals unless they simplify down to one of our integers. And then the largest set, which includes all of these sets, and if you can see, we're kind of building on the previous ones and even using the previous term or definition in defining the next set. And rational now includes all the numbers in between. And so this would be numbers that can be expressed as a ratio of two numbers, or I should say integers. And it does need to be integers. And we'll make a note that, so that would be a fraction, which would be a over b, where b doesn't equal 0. So a and b are going to be integers, and we should be able to express any rational number as a fraction. So for example, 1/3 is a rational number and it has integers here. 0 is a rational number. It's also an integer and a whole number. So 0 over 2. So the denominator can't be 0, but the numerator can be 0. So this actually simplifies down to 0. If we had 12, 24 over 2, that would be one way to express 12 as a ratio of two integers. We could have also chosen 12 over 1. And we're going to make a note here that decimals must terminate or repeat. So decimals must end, that's what terminate means, or they must repeat in order to be counted as rational, which then brings us to that classic number pi, which is not a rational number by definition. There are some fractions that are pretty close to giving us all the digits of pi, but there is not a fraction that's equal to pi, and pi does not stop and it doesn't repeat. Number two, we're going to place these numbers in the Venn diagram, and we're also going to finish labeling this. So rational numbers is the largest set, integers is the second largest set. We have whole numbers, and we have natural numbers. And we're going to place these in the most concise way, which means that, and we'll go through these and cross them off as we go, which means that 3/4, I'll talk about concise when I get to a good example. 3/4 is a fraction, and 3/4 would go here. We don't want to place it here because it's not an integer. It is a rational number that does not fall into the other subsets. So this is kind of a fancy Venn diagram. Let's go to 0.7, which repeats, and we're going to place 0.7 here as a rational number. It is not an integer, a whole number, or a natural number. All right, 8. So 8 is a natural number. It's a whole number. It's an integer, and it is a rational number. But we're going to place it in just one spot. And 8, if we think about our sets, it first showed up in natural numbers. So by placing it in natural right here, we're also saying that since this is nested within whole numbers, integer, and rational, by just writing 1/8 here, it actually falls into all the sets. And that's what we're looking to do. So we're not looking to write 8s in all 4 categories, just in this subset, which implies it's in the other sets. This would be a good time to pause the video and try to place the other 5, and then watch me do it or skip to the end. Feel free to pause or rewind the video if I'm going too fast or you want to listen to something again. But if you think you got it, try the next 5 and then unpause the video. All right, hopefully tried those. 0 was a whole number. We'll place it here, which means that it's also integer and rational, but it's not natural. Square root of 9 equals 3, and 3 is a natural number. We're not going to talk too much about square roots right now, but the idea behind a square root is it's asking a question, which is what two identical numbers when multiplied equal 9? And it's 3 times 3. And so this just equals square root of 9 equals 3. -6 is an integer and a rational. 2.15 is a rational, and 3.5 is a rational. So there's our completed Venn diagram, and my color choices have really no bearing on what's going on. I just happen to change colors. And we're going to skip down to the definition of a linear expression, which we're going to use throughout Module 1 and actually several of the other modules. Rational numbers are often used to create linear expression. A linear expression is a mathematical phrase consisting of numbers, variables, and or arithmetic operations. Next line will go right that describe a real world situation. And we'll put some examples. So we're going to write one that is 3x minus 5. So it has numbers, variables, it has an arithmetic operation, it has multiplication and subtraction, and we'll also notice that we don't have a variable that has an exponent other than the implied one, which makes this linear. Let's look at another example. What about one that isn't simplified, like 3x plus 7x plus 2x? We'll talk about how to simplify this. This would also be a linear expression. So something that wouldn't be linear would be 3x squared or 3x cubed. We'll kind of put an x through these. These are non-examples. Another example that would work would be just 6 or just x. So now we have 1, 2, 3. We have 4 different examples. Hopefully you have at least 2. And if the non-examples are helpful, then you can also include those.